Okay, today we're going to look at Chapter 8, Threads and Fasteners. Okay, we're going to learn how to represent fasteners and threads on an engineering drawing and how to calculate bolt and screw clearance holes. Key points: that threads are represented by thread symbols, not by a realistic drawing. Fasteners. Fasteners include bolts and nuts that are threaded, set screws that are threaded, washers, keys, and pins. Fasteners are not a permanent means of assembly such as welding or adhesives. Fasteners and threaded features must be specified on your engineering drawing. The threaded features are specified in the thread note. General fasteners, the purchasing information is given allowing you to order the correct fastener. Screw thread definitions. Okay, screw thread is a ridge of uniform section in the form of a helix. We have external threads, okay, like a screw, and internal threads, like the inside of a nut. External threads on the outside of the member. There is a chamfer on the end of the screw. You can see here that makes it easier to engage the nut. An external thread is cut using a die or lathe. This is a die. Okay, put it on the end of the rod and you screw it in. That cuts the threads in it, or you can do it on the lathe. Internal threads are on the inside, like in the side of a bolt. Okay, the internal thread is cut using a tap. Okay, we drill a hole in here and then we use the tap to cut the threads in. And if we're doing it by hand, we use a tap holder right here. The tap goes in to the tap holder. Definitions. Okay, we have the major diameter specified as a capital D. That's the largest diameter. Okay, in this case here, it's from here to here. It's the major diameter. The minor diameter is the smallest diameter, which would be down here and here. The pitch diameter is diameter in which a line cuts the spaces and threads equally. Okay, so here's our thread depth. The thread depth is the major diameter minus the minor diameter divided by 2. We take and cut that in half, and that is our pitch diameter. Okay, we have a crest. The crest is the very top of the thread. The root, of course, is the bottom of the thread. The side, strangely enough, is the side of the thread between the crest and the root. Okay, the pitch is the distance from a point on the screw to a corresponding point on the next thread. Okay, down here. Okay, the angle of the thread is the angle between the threads. The screw axis is the longitudinal center line. Okay, you identify these parts of a thread. Okay, major diameter, minor diameter, pitch diameter, the thread depth, the root, crest, side, screw axis, thread angle, and the pitch. We have right-handed threads. It advances when it is turned clockwise. All threads are assumed to be right-handed unless they're specified otherwise. Left-handed thread advances when it is turned counterclockwise. Types of threads. There are many different thread forms, shapes available. The most common are unified and metric. The thread form choice depends on what it will be used for, the length of engagement, the load, and things like that. Okay, here are some thread forms. This is a unified screw thread. This is the type that you're probably used to looking at. As for general use, here is an isometric screw thread. Looks just like it, except it's isometric. We have a square thread. A square thread is ideal for power transmission. we have an Acme thread. It is like a square thread, but it's on an angle, which makes it stronger than a square thread. You may see an Acme thread on a thing like a vise. A buttress thread is designed to handle heavy forces in one direction. Okay, I don't know if you've ever seen one, but the old-fashioned jacks in a car had buttress threads on them. Manufacturing. Internal threads. First, a tap drill hole is cut. Okay, so there is a drill. We drill a hole inside of here. Okay. The tap drill is a little bigger than the minor diameter. Okay. The external threads would not fit if the tap drill was not bigger than the minor diameter. It would obviously not fit, so it has to be a little bit bigger than the minor diameter. Okay, if you see here. Okay, there are charts that will tell you what tap drill to use when you are creating a tap. Internal threads. Okay, when that hole is created, then threads are cut using a tap. Okay, the tap drill hole is longer than the length of the threads. Why? Okay, because we have incomplete threads here on the tap. Okay, so we usually leave approximately 3 useless threads at the end of here. Okay, so usually when we talk about the thread length, we're talking about from this distance to the last usable thread. Chamfers are cut to allow for easy engagement, both here and of course here. External threads, you start with the shaft the same size as the major diameter. The threads are then cut using a die or lathe. Okay, so we're going to look at drawing screw threads now. There are 3 basic ways to represent screw threads on a drawing: detailed, schematic, and simplified. The screw threads that we're talking about are in accordance to ASME Y14.6. Okay, the detailed representation is a close approximation to the appearance of an actual screw thread. There are external threads and our internal threads. Okay, what do you think the pros and cons to this are? Pros, looks good and you can tell that it's a thread. Cons, it takes a long time to draw, even with CAD. It takes a long time to draw, and even in 3-dimensional it's a little tricky. We'll look at them, but they're a little tricky. It is unusual to draw detailed representations of a thread. Okay, just get that out in the open. We normally don't do this because it's pretty, but it's not worth the effort. Schematic representation uses staggered lines to represent the thread roots and crest. Here you see we have the major diameter, okay, which is these long lines and the outside lines. Then we have the minor diameter, which is the short one here. We have the chamfer, and then the pitch is the distance between the long lines. Pros and cons to that: it's nearly as effective as a detailed representation. Again, it kind of looks like a thread, and it's much easier to draw. The cons are, it still takes a while to do it. Okay, we won't do many of these at all. Okay, the rules for schematic representation: should not be used for internal threads or sections of external threads. Okay, we do not show the dotted lines here, for example. Okay, for a schematic thread, looking down on it, you see the major diameter as a dotted line and the minor diameter as a single line. On this side you will see, depending on what we have, either the internal thread or that chamfer there. Okay, but we do not show these hidden. Simplified representation. Simplified uses visible and hidden lines to represent the major and minor diameters. Again, we just draw the major diameter, then we draw dotted lines for the minor diameter. Much easier to draw. Okay, it is one of the few times when we draw sections that we do put dotted lines in here to show that those threads exist. Okay, looking at the top view, you'll see either the minor diameter or the beginning of that chamfer, we normally draw them the same when we're drawing a simplified, and then the major diameter. Pros and cons of this: it's very simple and fast to draw. Cons: it does not look like a thread. It is so common that people recognize it as a thread. In Inventor, it is the default. Okay, when we draw a thread and we make a drawing of that, it is going to be shown as a simplified representation. Okay, you save on time, you save on ink. Okay, and again, it's a well-known standard. Okay, so anybody that sees this knows that represents a thread. Simplified internal threads are shown dotted like this. Here is a section of it. Again, we have the dotted lines of the major diameter. Okay, the bottom of it, you will see the minor diameter as a solid line. You'll see the major diameter as a dotted line. Here you'll see the two lines for the chamfer and for the major diameter. Okay, again, we usually draw 3 times the pitch here, the useless threads that we talked about, and then we draw just an angle there. Okay, and this is our thread length. This line right here represents our thread length. That is what we call out on the drawing. We don't worry about this here. We don't really care. We don't care what that length is. Usually at the bottom there is a 30-degree angle. That takes care of the drill bit. Drawing screw threads. Okay, there are thread tables in the appendix, so we can look them up online. That will give you the value of the pitch, the minor diameter, the major diameter, of course, the tap drill diameter. If the screw thread tables are not available, the minor diameter can be approximated as 75% of the major diameter. Again, remember, we're only representing threads. We don't really draw the threads. Okay, drawing them in Inventor. Okay, let's say we want to draw a number 1024 thread. Okay, here is a chart, not from your book, but from a site on the internet. Here is a 1024. The basic major diameter is 190. Here's the major diameter over here, which is going to be the basic diameter. Okay, the minor diameter is between 145 and 155, 156. The pitch diameter, okay, we really don't need to know. Okay, we never need to know that. We will need to know the pitch, and we'll talk about that in a little bit. Alright, so let's go into Inventor. Okay, I've already opened up a standard drawing. Okay, I'm going to go here and I'm going to draw an external thread. So I'm going to go here and I'm going to draw a circle, and we said that diameter is 190. And I'll finish the sketch. Now I'll just take and extrude this, and sure, an inch will be fine. Okay, to draw a thread in Inventor is one of the easiest things you can do in Inventor. We go up here and we pick thread. Okay, and they ask us stuff, and we don't care about 90% of that. We just pick this and it automatically says, okay, it is 190, so that's a number 10. Okay, now there are different values. There's 1024s, 1028s, 32, 36s. We said we wanted a 1024. Don't worry about the class right now, whether I'm left-handed or right-handed. The thread, okay, the depth Okay, it just here it has the entire depth. So I'll just pick OK. And there is my thread. Now, this is not a thread. This is a picture of a thread that is wrapped around this. It is fine. Okay, there's no problem using that. Okay, now if I want to draw an internal thread, okay, start a new sketch. Maybe I'll start it right here. Okay, and I'll just make a block here, and I'll pick OK, and I'm going to put a circle here, and I'll make that point 190. Okay, and I will finish the sketch. Okay, I'm going to extrude this. I'll go up like that, and I'll go up, I don't know, 0.75. Okay, so there I have it. If I want to make an internal thread, I click on this right here and I pick thread. Again, it's going to pick the correct one. And I'm going to pick OK. Now we can also use the hole command, and I'll show you the difference. I'm going to put one here. Okay, now I want a tapped hole. I want a regular hole. I want them to be ANSI. Go down here and I'll find a number 10, which is right here, 190. And I will go through the entire object. Now, it's going to leave that extra thread that I told you about. So if I go 2 and pick the bottom of the surface, notice it made it a little longer, I believe. Okay, and I'll pick OK. Alright, so now again I have a picture of a thread. Okay, that's all I have. Now I'm going to file and save this. Now I'll just call this 1024 thread and call it anything I want. Now, if I go to look at a drawing, I'm going to open up my title block. I'm going to pick OK. Okay, and I'm going to put that here. Okay, so I can put one here. Let's see which top view I want. Yeah, let's do this. Let's go this way. And I'll draw a side view over here. And I'll pick OK. Okay, here is our holes. You'll see the way our holes are tapped here. Okay. See the way this is a simplified. This is a simplified. Now, when I created that tapped hole here using the hole command, didn't work out quite right. Now, if I go here to annotate and I go to dimension and I pick this guy, okay, it just says 190. If I go here and pick this one, it'll say 240. Okay, not exactly what I'm looking for. Okay, but if I go to the thread, the one that we made with the thread, now notice it does make it correct. Okay, it's a 1024 UNC. Okay, and I made a 3/8 depth. That's why that's shown here. Now I can also, if I go to here and click on this guy, it shows that thread right there. Okay, so sometimes it is better to show or to create it using the hole command than to create a hole. Okay, I also needed to make this different size. That's the wrong size, but I think you can get the idea of what we're looking at here and how easy it is to draw our thread. Now, if I go here and project this guy so I can see that, where is it? Here it is. Right here. I'll move him over here. Maybe. I'll move him over here and let's take a look at him. I'm going to change this. I'm going to make sure that the thread features are shown. Okay, and again, that's just a picture of a thread and it is fine. Okay, no reason not to do that. All right, we're going to look later and see that if we're using not a custom made thread like these were, but if we're using screws and nuts and bolts, okay, those are automatically on our in Inventor, and we can use them and they're much easier to use even than what we did here. So let's talk about unified threads. Okay, unified threads are inch threads. Okay, they are inch. After drawing a thread, we need to identify the size and the thread form and the thread note. Okay, here is the thread note. You can see that it is similar to the one that showed up in Inventor. Okay, if I go here to Inventor, this is 1024 UNC-2A. Okay, a little different, but it's close. This is a half 13 UNC 2A RH. This is the thread note. Okay, and again, the drawing here isn't that important as long as it's close to the right size and looks about right. The thread note is what is important. Okay, the thread note has this information. Okay, the first is the major diameter. Okay, so this is a 1/2. This is 3/8. That is the major diameter. Notice we point to the major diameter, not to the solid hole, but to the threaded hole. Okay, then we have the -24 in this case. That is threads per inch. Okay, it is how many threads per inch. UNC is the thread form and series. Unified National Fine. Okay, this is the thread class, the 3. The B is whether it's internal or external. Okay, this can be LH for left-handed or RH for right-handed. If it is right-handed, we normally leave this off. We use this symbol for the depth, and this is how deep it would be. Okay. Alright, so again, major diameter is the largest diameter. Threads per inch is the number of threads per inch for a particular diameter. Okay, the threads per inch is equal to 1 over the pitch. Okay. The thread form series is shape of the thread cut. UNC is Unified National Coarse. That is for general use. We have Unified National Fine. It's used when a high degree of tightness is required. The number of threads per inch are usually greater. Then we have UNEF, which is extra fine. Okay, so if you have a limited engagement, okay, so like something like sheet metal, okay, you have a real thin piece, but you want some threads in there. The thread class is the closest of the fit between two mating threaded parts. Okay, 1 is a generous for rapid assembly and disassembly. A 2, and this one said 3, but a 2 is normal production. 3 is high accuracy. Okay, if this number here is an A, it is an external thread. If that is a B, it is an internal thread. Of course, again, RH is right-handed, LH is left-handed. The thread of the depth is given at the end of the thread note and indicates that the thread depth for internal threads. Okay, this is not a tap drill thread. It's the depth. It is the depth of the threads themselves. Okay. Again, for these, the thread class, you normally put that on. It is assumed to be a 2. All threads are assumed to be right-handed. Unified National Coarse thread components. Okay, so identify the components of the following UNC note. Okay, so here we have a 1/4 20 UNC 2A RH. What is the 1/4? That's the major diameter. What is the 20? 20 threads per inch. The pitch is 1/20 or 0.05. UNC, thread series. UN coarse. 2 is normal thread class. The A means they're external threads, and it is a right-handed thread. Okay, let's take a look at identifying a thread note. Okay, so here we have this, and we want to write the thread note for a number 10 fine thread. Okay, we'll look in the appendix in our book. Here is the appendix in our book. So we have a number 10. Here's a number 10. Okay, here is the fine. Here's coarse UNC, fine UNF. There is no extra fine for that. Okay, so we write 10-32. Again, here is 32 threads per inch on the fine. UNF, Unified National Fine. Is the major diameter 10 inches? Of course not. Okay, the major diameter is 0.190. Okay, so we have number sizes from 0 to 12, and then we have them in fractional sizes. Okay, what is the minor diameter? Now if I look at this one, okay, I don't see no minor diameter, but you can approximate the minor diameter by taking the major diameter minus 1.0825 times the pitch. Okay, so D minus 1.0825 times the pitch. Okay, the pitch we said is 1 over the threads per inch, so we can take 0.190 minus 1.0825 times 1 over 32, or divided by 32, so our minor diameter would be 156. Okay, we talk about metric threads a little different. They're actually a little easier, especially with the numbers. Metric thread note contain a pitch diameter tolerance. What is the pitch diameter? Let's see. Okay, the pitch diameter cuts the thread at the point where the distance of the space is equal to the distance of the threads. Okay. Alright, when we talk about a metric thread, we put an M there to tell you it's metric. Here is the major diameter, so we don't have to use any books. We know the major diameter is 6 millimeters. Here is the pitch. The pitch is 1. Okay, now it's a little different. Here we have the tolerance class. Again, left-handed or right-handed. Right here, this 5H is the pitch diameter tolerance. Right here is the crest tolerance. Okay, divided by the minor diameter. Okay, these are going to be in the chart. We don't need to figure any of those out. And this, of course, is the thread depth. Okay, again, metric form, major diameter, the pitch, the tolerance class. Okay, placing an M before the major diameter indicates that it is metric for the third time. Okay, again, major diameter is the largest diameter. Pitch is millimeters threads. Pitch is millimeters threads per inch. Tolerance class describes the looseness or the tightness of the fit between internal and external threads. Again, the number is the tolerance grade, the letter is the tolerance position. Again, we'll get these from the book. The tolerance class, smaller numbers indicate a tighter fit. Tolerance position specifies the amount of allowance. Uppercase letters are internal, lowercase are external. Class, 2 classes of metric fits are generally used. 6H, 6G is a general purpose. Excuse me. 6H, 5G, 6G is a closer fit. A tolerance class of 6H, 6G. This one is assumed if it's not specified, and we usually will say it's not specified. Okay, RH and RLH, left-handed, right-handed. Depth of the thread again is the depth of the thread, same as we looked at before. Okay, again, tolerance class of 6H, 6G is assumed. and the threads are assumed to be right-handed. Alright, so let's try some components. Alright, so identify the components of this, which is an M10 by 1.5 4/8/6H right hand. Okay, the end M is metric. Okay, the 10 millimeters is the major diameter. 1.5 is the pitch, millimeters per threads. 6H is the pitch diameter tolerance. 6H is the crest divided by the major diameter. Is it internal or external? It is external, so it's lowercase, and it is right-handed. Okay, and again, we have standard thread tables in the back of the book, or get them online. Okay, for a number 16 or 16 diameter internal metric thread, what are the two available pitches? The tap drill diameter and the corresponding major diameter for the mating external threads. Ooh. Okay, so find this page and here is our answers. Okay, so the external thread we know are approximate minor diameter. D minus 1 is the minor diameter, and here is the pitch. Okay, so the pitch is 2 and 1.5. Okay, nice thing about this, it's 2 and 1.5. Tap drill diameter. Okay, again, this is nice, gives us the tap drill, 14 and 14.5. Minor diameter, 13.6, 14.2. Again, you can figure those out. Okay, so if we have a 16 diameter internal metric thread, if the pitch is 2, we have one if the pitch is 2, one is the pitch 1.5, which is a finer thread. Of course, it is the 1.5. Write a thread note for a 16 millimeter diameter coarse thread. Okay, M16 by 2. Okay, I don't know if this shows it or not. Back to here. Okay, on M16, here is the coarse thread, which is a 2. The fine thread will be 1.5. Okay, I'll take a look at drawing bolts. Okay, we can draw the bolts if we're doing them on a 2D drawing like this. Okay, we are not going to. We're going to look at a better way to draw it because we're going to draw them in 3D. Okay, but if you ever need to draw one, just get this out. The height of this is going to be 2/3 of the major diameter. This is 1.5 from the flat to the flat is 1.5 times the diameter. Now you could use that once in a while. We have an angle here from that corner 60 degrees and 60 degrees, another one 60 degrees. And then we take this radius from there to there, and where these two meet, we take that radius there and there. Okay, not too bad to do. So we will take a look at drawing one a little bit later. Bolt and screw clearances. Bolts and screws attach one material with the clearance hole to another material with the threaded hole. Okay. Here is the clearance hole, here is the threaded hole. Size of the clearance hole depends on the major diameter of the fastener and the type of fit. There are 3 basic fits: normal, close, and loose. Okay, here's a table in the back of the book, and these are normal fit clearances. So depending on the size of the screw, okay, so from anywhere from a number 0 to a number 4 would be that diameter plus a 64th. Okay, from a number 5 to 7/16, the diameter plus 132, 1/2 2 7/8, 9, the diameter plus 1/16. Sometimes bolt or screw heads need to be flush with the surface. This can be achieved by either using a counterbore or a countersink. This is a counterbore. This is a countersink. Okay, this is for like cap head screws. This is for flathead screws. Okay, counterbores are holes designed to recess bolt or screw heads below the surface of the part. Typically, the clearance here for the counterbore is the height plus 1/16, or if you're doing metric, 1.5. Okay, that's for the height, excuse me. The clearance for the counterbore itself will be D1, which is the diameter of the head, plus 1/8, or 3 millimeters. Countersink are angled holes that are designed for recessed screws with angled heads, typically C1. Across here is D1, the diameter of the head, plus 1/8. There are other tables in the back of the book for the clearances. Okay, going to look at right here. What is the normal fit clearance diameter hole for the following nominal sizes for a quarter? Okay, and that is between the number 5 and the 16th. That is the diameter plus a 32nd, which would be 9/32 or 0.281. For 3/4, okay, it would be diameter plus 16th, 13/16 or 0.812. Okay, so let's say we have a 5/16-18 UNC socket head cap screw. Needs to go through a piece of metal in order to screw into the plate below. The head of the screw should be flush with the surface. Okay, looking in our appendixes, the head diameter. Okay, here it is. Our head diameter is the diameter plus or times 1.5. That's going to bring us to 5/16. So 5/16 times 1.5 is 469. Max head of the height is the same as the diameter, 5/16 clearance hole. Okay, 5/16 got a normal clearance hole. Okay, should be 17/32. The counterbore depth, okay, which is just greater than the height. Okay, and sometimes a good number to use is like a 16th, so that would be 3/8. Okay, same thing if we have an 8/25 flathead countersunk hole, flathead. A countersunk head metric cap screw goes through a piece of metal. Clearance needs to be flush with the surface. Okay, again, looking at our tables, our major diameter is 8. Our head diameter is, there's 8. Okay, the head diameter is 17.92. Okay, 17.92. The countersink diameter is, should be Y, 17.92. And the clearance for diameter hole will be right here. Here is our clearance hole. So that is going to be 8.4 right there for a close fit. Standard parts. Standard parts are parts that are purchased. We don't need to draw them. Okay, we use a standard part sheet, just gives enough information for us to be able to purchase the item. Okay, so here we have our parts list. These are our standard parts. This is how to find it on the assembly drawing with the number. This is how many required, the part number, the name, the size, series if it has one, the material if it has it, and any special requirements. Okay. Okay, so now we're going to do some demos, and actually the first one I want to look at is going to be looking at, where'd it go? Right here. And I'm going to draw this, and I'm going to show you how Inventor will figure out what these clearances should be. All right, so I'm going to show you some stuff that we haven't done yet, but I want to show you how Inventor can do that, and we'll look at how we would do it without using that. So we're going to take a look at creating our exercise here, where we want a 5/16-18 UNC socket head cap screw. Go through a piece of metal in order to screw into a plate below. The head of the screw should be flush with the surface. Okay, so that's what we're going to take a look at. So I'm going to go into Inventor, and I'm going to start a new part. Okay, I'm going to make a standard inch. And I'm going to draw a plate. Okay, so I'm going to go into your sketch, I'm going to go to top view. I'm just going to make a rectangle from the center, right there, like that. Click OK, and I'm going to dimension from here to here, and make that an inch. We'll make it something nice and easy. We'll make that an inch. Okay, and I'm going to pick finish sketch. I'm going to extrude this guy up, and I'll make that, I don't know, maybe a 1/2 inch. Okay, so this is going to be our top plate, and our top plate wanted to have a countersink because it said that the bolt must be flush to the top. So I'm going to use the hole command. Okay, I'm going to pick here, and I want it from that edge 0.5 and that edge 0.5. Okay, now what I want here is I want a clearance hole, I want a counter bore, okay, and I want a counter bore for a socket head cap screw, and I want that to be what I say 5/16 right there. Okay, now I don't have any threads and I want that to go completely through. Okay, so I pick OK, and now I have my piece with the counter bore in it. Okay, I'll go up, I'll do file, and I'll pick and save this. Okay, and I just have this folder here, and I'm going to put top plate. Okay, now what I'm going to do is make another one. I'm going to start a new sketch, and this will be for the bottom plate. I'll go here, oops, and I'll make that the same size. Make that one, make that one, oops, try that again, make that one. Take, and I'm going to extrude that, and we'll do 0.5 again, and I'll pick OK. Going to use the hole command. Right about there, I'm going to put it 0.5 from that edge, 0.5 from that edge. Now I want a tapped hole, but I do not want a 3/8. Okay, notice it gives me all the different 3/8, so I have to go up to here, and I have to pick 5/16, which is about 312. There's 5/16, 18. Okay, now I want this to go a specific depth, and I want this to go, we'll go halfway through. Oh, wait a minute, that was 0.5. We'll go 0.25, And then what I want here is I want that to the thread. Okay, so I want about 2 or 3 threads here. Okay, for a /18, okay, that is 18 threads per inch. If I take 1 divided by 18, that gives me the distance of my pitch was at 0.055. I'll multiply that times 3. Okay, so that's 166 plus 0.25. So that's about, let's make it 400. We'll make this 0.4. Okay, again I'm going to check I got the right tap size, and I'll pick OK. So now you see that it tapped the hole. Okay, if I go here to view and change this to a wireframe, okay, I can see there is my blind hole. Okay, I'm going to go back to here, change this back to shaded. Okay, and I'm going to take and I'm going to file and save this as, and this is the bottom plate. Okay, now what I want to do is I'm going to, so I have my sizes, I'm going to go and make an assembly. Okay, and I'm going to place my bottom plate in first. I'm going to right click, place grounded at origin, pick OK. I'm going to place my top one, my top plate here. I'm going to pick open, slap it there, pick OK. Okay, now I'm going to put these together using the join command. What I want to do is I want to rotate these guys around, and I want to join the center point here to the center point here. Whoops. Here. And I want this to be rigid. Pick OK. So now I have my 2 plates together. Okay, now what I'm going to do is I'm going to place from the content center. Okay, so here you'll see I have my content center. I have all my parts. I can go to fasteners. I want bolts. Okay, I want a socket head screw. Okay, now I want to find a socket head screw that is inches. Okay, I should be able to go here and say socket head screw inches. Or maybe not, maybe if I just put inch. Okay, so now I can pick one of these if I want. So let's see, here's a socket head cap screw. So I'll double click on that. Okay, I'm going to click here and it'll give me the option of what size I want. I want a 5/16. Now, do I want UNC or UNF? Well, if I don't remember, I can go here and a 5/16. Here's UNC, which is 18. Okay, so I want a UNC. UNC. Now I want the depth of that. Okay, and I'll make it the depth that I put there for the thread, which was, let's see, we'll pick, okay, we'll pick 375. Okay, and there it is. I'll right click and I'll rotate this around. Okay, and I'll put it there. Now I'll take and I'll join these two together from here to the center of that hole right there. Okay, again, if I go here to view, change just the wireframe, take a look at the right size. Could have made that a little bit longer if you wanted to. So I can go right here, right click, and change size. Okay, so actually maybe I want to go about a 1/2 inch. I'll pick OK, and that looks a little bit better. Can also go here, and under view you'll see half section view. Now I'm going to go to half section view, and it wants to know what I want to look at. I'm going to go to origin, and I can pick one of my planes. Let's pick this plane right here. Okay, and you'll see that it cuts it in half, and I'm going to pick, whoops, come on, stop moving on me. Okay, I can take and I can move this. Okay, maybe about halfway there. Pick OK. Now I can see I have my cutaway view, and you can see the clearance for the head. If I go to the front view, see the clearance for the head. There's a little clearance for the screw in this one. You can see it right here. Okay, that little shaded part. Okay, so that is how we would create that. Okay, I could take now example and pick open, and let's open our A size drawing. Okay, now I can take base. Yeah. It wants me to save that assembly because it thinks I want to use that. Okay, I don't for now, so I'm going to go here, and I'll go to where I put that, which was under project, threads, the assembly, and here, for example, here is the top plate. You can pick OK. Maybe I'll start with this view. I can make that a little bit bigger, I think. And then a side view right here. Okay, and actually the side view really isn't going to help us at all, so I'm going to get rid of that and just put this one here. I'm going to pick OK. There it is. Now I'll make a section view. I'll go halfway here. Continue. There's my section view. Go up to annotate, and I can put some center lines in here. Put a center line down the middle of this guy. Okay. Maybe move that guy out of the way. Now I can take and I can dimension like from here to the center. And then this one here. From here to the, whoops. From here to the center. This one here. Okay, if I go to hole and thread, since I made it with the hole command, okay, I have 0.33 through. It's a countervore 0.5553, and it is 3.1 deep here. Okay, I put one more dimension. Here I have that one, and there is my top plate. Okay, I'll pick save as. Put it where it belongs. That's the top plate. I can open up another one. guy around there. We'll make him 2 to 1. Okay, and we'll put a section through here just so you can see it. I'll go here, here. I'll put a section view right there. Okay. Again, I can dimension it. Okay. From here up to here, here to the center. Put a center line through there. Dimension from here to the center. And this line here. Okay. Dimension my tapped hole. And then maybe the thickness here. Alright, so that is how we would create those in Inventor. That is the end of threads.